Hi, good morning. Good morning. Okay. So we are done with the theory for this topic. I thought we'll do the remaining questions today. And then the last one part was there. One last part, the ultimate fate, we spoke about it, right? Yeah. Life cycle of a star that you do for all of it. Fine. What are the questions? Did I assign anything in particular? No. Nothing in particular, is it? Okay, guys, turn to page number 34. Page number 34, question number 20. Page 34, question 20. Read the question. Page 34, question 20. In the 16th century, the astronomer Tycho Brahe made measurements of stars in the night sky. He measured the angle of a range of stars. He measured the angle of a range of stars above the horizon. For each star, he measured the angle over a period of time to determine the parallax effect. Describe how stellar parallax is used by astronomers. Can you go to the note where we spoke about parallax measurements? Where we spoke about trigonometric parallax in the theory view, page number 7. Read that. Okay. Write the answer. Describe how stellar parallax is used by astronomers to find distance to the stars, to the nearby stars, right? This method is used to find the distance to relatively close by stars. So, right, the close by star is viewed from two positions. Six months apart. 6 months apart. Full stop. The change in angular measurements. The change in angular measurements with respect to the fixed background stars is recorded. Full stop. Then using trigonometry, the distance, then by using trigonometry and the radius of orbit is the radius of orbit of the Earth around the Sun then using trigonometry and the radius of orbit of the Earth around the Sun, the distance to the star is calculated. Now read the answer. Okay. Okay. So guys, this is what was done when using this method, stellar parallax or trigonometric parallax. What you do is, when the Earth is at one position, you take the angular measurements to the star with respect to the background stars. You focus at a background star and you get this position of the star and measure the angle. And 6 months apart, exactly the Earth will be on the other side of the Earth. And then you take the measurement. And then by measuring this angle and by knowing this distance, you can find the distance to the star from the Earth. This can be measured. Okay. So that is what I have given in the answer for a 4-marker. This can be tested again and again, and they have done it. So this is what you have to do. This is how it is done. You have to take the measurements to the close by star with respect to the background stars, 6 months apart. And then by knowing the radius of the orbit and using trigonometry, you can find the distance to the close by star with respect from the Earth. Right. The next one, part 2. He concluded that the Earth was motionless at the center of the universe, as he was not able to detect any stellar patterns. He decided, no, the Earth is motionless. Suggests why he was not able to detect any stellar parallels. What could be the reason? Or the angle he measured is too small. It cannot be detected in that. In that note, it says, right, what is the minimum angle that is needed? It was there, right? When the theta is extremely small, you will not be able to. When the theta is too small, you will not be able to recognize it. Okay. So they're asking why he concluded that it is motionless, right? The angle measured or the angle involved is too small. Since the stars were too far. Since the stars were too far. Okay. Well, now, do you understand the point? If the stars are extremely small, that angle will be very, very small. Okay? I mean, if the stars are extremely far from each other, then that angle will be very small. Yes or no? Like I can give you a simple example like this. Now let's say this is the Earth. Okay. Sun here. Fixed star is here. Let's say the distant stars are here. For an example, the distant stars are here. Is the position. Then this angle we are speaking is this angle. Okay. For the same thing, now the Earth is, Sun is here, the Earth is here, the star that the close by star is here, the distant stars are here, background stars are here. Okay. So simple trigonometry, the further it goes, this angle will become smaller. Okay. So if it is far and this angle will become extremely small. If the distance between these two stars is, it's going to be thousands of light years away. If it is beyond a certain level, this angle will be too small that it will not be able, you can't measure it. That is the reason why he has concluded it is motionless, because the distance between the stars is too far. The angle is too small. He was one of the first astronomers to observe a supernova. Supernovas are used as a type of standard candle. State what is meant by standard candle. What is a standard candle?
It's a star with
a star with a known luminosity. Okay. A star with a known luminosity is what you call a standard candle, right? It is a star with a known luminosity. It doesn't have to be a star itself. You can call it any stellar object. A stellar object with a known luminosity, yes, most of the time it's a star. A stellar object with a known luminosity. That is what you call a standard candle. You know its luminosity. Describe how the standard candles can be used to determine the distance to nearby galaxies. So guys, if you know the luminosity, we have this equation. Intensity is equal to intensity is equal to inverse proportional to square root was there, P over 4 pi r square. So if you know the intensity which is falling on the Earth, using the inverse square root, since this is known, we can find the R. We did some calculations to find the distance when the luminosity is known. So for a 3-marker, they ask you to explain it. Describe how standard candles can be used to determine the distance to nearby galaxies, right? Since the luminosity is known, the intensity of the radiation from the standard candle should be measured. Then by using inverse square law, then by using inverse square law, then by using inverse square law, the distance can be calculated. Okay, read the answer again. No, read it for me to hear. Can you read the answer? Correct. It's a 3 mark. There's then turn to page 20, sorry, page 40, question 23. Same thing they have given for a 6 marker, but slightly different. Read the question. The average distance between galaxies, is many times greater than the size of our galaxy. Astronomers use standard candles to determine the distances to other galaxies. Describe how astronomers determine the luminosity of a standard candle and can use this to determine the distance to a nearby galaxy. Describe how astronomers determine the luminosity of a standard candle and can use this to determine the distance to a nearby galaxy. It's a 6 marker. Now here they have given 2 parts. One is describe how the astronomers determine the luminosity of a standard candle. Okay. And then using that to determine the distance to a nearby galaxy. 6 marker. Write the answer. By using stellar parallax. By using stellar parallax. The distance to a nearby star or nearby standard candle can be calculated. Stop. Then by measuring the intensity, of the radiation from the standard candle and using inverse square law. inverse square law, the luminosity of the candle is calculated. Full stop. Then the standard candle is located in the nearby galaxy. Full stop. Since its luminosity is known now, come on, the distance to it can be calculated using the inverse square law. Guys, read the question and read the answer again. When you are measuring the distance to the nearby star, yes. So it's a 6 mark. Now the question is the average distance between galaxies is many times. Fine. Astronomers use standard candle to determine the distances to other galaxies. Describe how astronomers determine the luminosity of standard candle and how it can be used to determine the distance to a nearby galaxy. So what we do is we pick a star close by. No need. Okay, so we pick a star at which is close by to us, and we find its luminosity. Okay, how do we do that? That is by using the stellar parallax. By using stellar parallax, the distance to a nearby standard candle can be calculated. Then by measuring the intensity of the radiation, and by using from the standard candle and using the inverse square law, you find the luminosity of that standard candle. You calculate it. By taking the, maybe at multiple points, you take the power divided by the area, that will give you the intensity. You can get the, what I'm saying is the intensity, power per unit area. So you can measure the power which is falling and get the intensity. Then using the inverse square law, you can find the luminosity of this. Okay. By using, so then you know the luminosity of it. You search for a star in a nearby galaxy which has the same luminosity. Okay, which looks almost the same like this. So then this and that star has the same luminosity. Okay. First, you find the luminosity of a star which is closer to you using stellar parallax, using trigonometry. Okay. Intensity will be different. Correct. So we find as standard candle is something with the known luminosity. So you find the luminosity of this and you search for something which approximately has the same luminosity. Yeah. Then using the inverse square law, you can find the distance. They're asking to find the distance. Definitely. Intensity will be different. No, we can't measure that. No, the luminosity. So the luminosity is going to be luminous intensity you can measure. If you can get the power per unit area, you can measure the intensity. Hold on. Hmm. Standard analysis calculator. Yeah, using Green's law. Hmm. And find the distance. Hold on. Then you need to know the temperature.
That's it, yes, can you?
Then then you have to get lambda max into P is a constant. Then you need to hold on. Okay, then you have to get the wavelength of the maximum intensity. Then you should know the temperature of the nearby stars. Hold on. You know the K, no? You know the K. You get the, you have the graph of luminosity versus lambda graph is there. So when the luminosity is known, you can get the temperature. Again, listen. When the luminosity is known, you can get the temperature. So by taking the temperature and using this equation, you can find the R. No, that graph is available. No? Luminosity versus. Yeah, no, lambda into T is anyway a constant. Hmm? No. Keep on. The graphs will be different, no? Hold on. You see, if you go check question number 829, check question number 29. It is a calculation of that, right? The same question calculation. A standard candle in the near galaxy M81 has a luminosity of 14,800 times. Okay, read the question carefully. The luminosity of the sun. The luminosity of that standard candle is 14,800 times the luminosity of the sun. The intensity of radiation received from the standard candle, intensity of the radiation received from the standard candle is measured at the top of the Earth's atmosphere. Is this much? The intensity is measured. So there is a method of measuring the intensity. So that means the intensity is known. Then the intensity equals L over 4 pi r square. The intensity is known and the luminosity is known. You can find the R. Definitely different. But there is a measuring method of intensity. Correct. Okay. So that is exactly the same calculation is what given here. They are asking you to calculate the distance from M81 to Earth. So you know the intensity equals luminosity of 4 pi d square. Intensity is measured. Luminosity is 14,800 times the luminosity of sun, or 4 pi d square. Okay. So go back to that answer. Maybe you can add another small part, say the standard candle is located in the nearby galaxy. Since its luminosity is known now, the distance to it can be calculated using inverse square law. You can add another point, the intensity of the radiation from the candle at the Earth's surface is measured. Okay. Now, now read the answer. Use standard chemical measure. Close by star. No. Or close by star. For another galaxy, you can't use this method because the angle will be too small. You can't use it. Stand here. Close by stars. For another galaxy, you can't do that. You have to find the distance to another galaxy. This is the method you use. You find the distance to a nearby star, and based on that, you do the calculation using inverse square law. Okay. Others, please read the answer, and if you have a question, you can ask.
So how do they measure power?
By the amount of energy falling per unit time.
How do you measure that?
There should be definitely method available to measure the energy.
Example.
I don't know what instrument they use at astrophysics level, so they definitely should be having that. Okay. Right, guys. Question 24 on the page 41. We have done the part A. Part B, read the part B. The graph shows how Z. What is Z? Redshift. The graph shows how Z for light emitted from a galaxy varies with the distance the light has traveled in reaching the Earth. Okay. A light year is the distance traveled by light in 1 year. Determine the distance from G and Z level has traveled in reaching the Earth in meters. 1 is 3.15 × 10⁷ seconds. Distance the light has traveled. That means basically the distance, determine the distance the light has traveled in reaching the Earth in meters. Okay. Now we have, it's connected to the previous part. In the previous part, we calculated the lambda naught. How much is the lambda naught? 1006. Read the first part, guys. Redshift is Z is known 10.96. GN-Z11 is one of the most distant observed galaxies in the universe, and a redshift of 10.96 has been detected by Hubble Space Telescope for radiation from this galaxy. Z is 10.96. So when the Z is 10.96, calculate the distance traveled, which is about how much is that? 13 point. They're like 13.5 or 13.6. No? According to the scale, it's 13.6. What is the unit given? 13.6 into 10 to the power 9 light years. 13.6 into 10 to the power 9 light years. So you need to see what is the distance traveled by light in 13.6 into 10 to the power 9 years. Okay, which is 13.6 into 10 to the power 9 into 1 light year is given. The speed of light will be 3 into 10 to the power 8 into 3.15 into 10 to the power 7. One light year is the distance traveled by the light in 1 year, which is 3.3 into 10 to the power 8. The distance traveled per second multiplied by the number of seconds per an year, 3.15 into 10 to the power 7. How was that? One 1.29 into 10 to the power 26 meters. Okay. Have you got this answer? The recently launched James Webb Space Telescope is designed to operate in the infrared region of the spectrum. The telescope is designed to operate in the infrared region of the spectrum. Explain why this will be helpful for studying very distant galaxies. Why? 2 marker.
This is not travel. Measure.
Okay, guys, very distant galaxy means, according to Hubble's law, that means it's traveling faster. Further they are, faster they are traveling. Correct? Faster they are traveling means, that means the higher will be the change in wavelengths, according to Doppler effect. Okay? So now, faster they are moving means, greater the change in wavelength means, by the time that wave reaches here, it might not be in the range of light. It can be in the range of infrared. So it is, there is recently launched James Webb Space Telescope is designed to operate in the infrared region of the spectrum. So the light which is seen, by the time it comes here, it might not be in the visible spectrum, visible light spectrum. It have gone passing that boundary, and maybe it is infrared. So it is good to have something which can detect it, infrared. So 2 marker, right? Further the galaxy is, high will be the change in wavelengths. High will be the change in the detected wavelengths. Full stop. So it can be in the infrared range. So it can be in the infrared range when it arrives at the telescope. When it arrives at the telescope. Sorry? Yeah, using that to detect it. Guys, question 27. Question 27, page 47. Read the question. The Hertzsprung-Russell diagram for a star cluster is shown. And the first part of the question was at a scale to the horizontal axis. So it starts from 20,000 and keeps reducing towards the right. That's how the HR diagrams are. Explain how this diagram can be used. Shows that the star cluster is not a young star cluster. You should refer to the groups of stars and their positions on this diagram. So guys, if it is a young star, the stars will be mostly falling in this stable. This is the stable part of the life cycle of the star. These stars are in the stable period. So you see a lot of stars in these parts, here and here. That shows now this cluster is not a cluster for a young star. This is a bit old. Maybe some stars are going towards the end of it. Okay. Did you all read the note that I sent you all about the life cycle of a star? Did you read it? Sure. Did you realize that there are two different life cycles? Okay, for whom and whom? Good, very good. For low mass and high mass. Good. Low mass means compared to the sun, the stars which have an approximately equal mass to the sun, they have a certain life cycle. And extremely heavy stars compared to the mass of the sun, they have a slightly different life cycle towards the end. Did you read it?
I didn't even get it.
Yeah, I sent it in the group. Yeah. I sent it, right? You ready? Ready? Fine. You ready now? Then tell me, after the stable period, what are the next stage after the stable period for a low mass star? It becomes a what?
The gravitational force reduces and
Okay.
the impacts and the heat increases.
Okay.
And some star.
Some-
The soonest
Huh? Yeah, it becomes a red giant. What does it become? Yeah. What does it become? Red giant. And then after that? White dwarf. The low mass stars become white dwarf. But then that is the heavy ones, not the low mass stars. But anyway, the question is not about that here. Using the diagram, the diagram shows that the star cluster is not a young star cluster. You should refer to groups of stars and their positions on this diagram. So write the answer. There are lots of stars. There are lots of stars. Which don't fall along the diagonal. Which confirms they have passed the main stable period. So the stars are old. So those stars are old. And they have reached the end part of their cycle or life cycle. Yeah. So that means most of them are not, I mean, not everything is falling in the diagram. No, young star cluster means you can consider to be most of them falling in the main stable period. No, so it depends on young means how young it is now. So what I'm saying is comparing to if all the stars are falling here, that means they are still in the main stable period. So that means relatively they are young. So what I'm saying is these stars are gone passing that. So that means they are not young anymore. They are towards the dead end of their life cycle. Right, the next one. In the early 20th century, Edwin Hubble observed that Andromeda Nebula. He saw stars similar to the stars in our galaxy. One star he saw was a standard candle known as V1. Describe how measurements of this standard candle could demonstrate that the nebula is not a nearby star cluster. How can you show that it is not nearby? One star he saw was a standard candle known as V1. So it is a standard candle. Okay. Describe how measurements of this standard candle could demonstrate that the Andromeda is not a nearby star cluster. Can you write an answer for this? You know, it's a standard candle. So basically, you should write the procedure of measuring the distance to a standard candle and then conclude that it is not nearby. Write an answer. Right? Why do you use this is something in our different galaxy. We observe the star similar to the stars in our galaxy. That means it's not referring to some other galaxy. We can't use that. You know the you know you measure the but then you need to have something at the background of that is but yeah, it's not really my stuff. And that's you are getting 3 marks, right? 4 marks, right? So the conclusion is that distance is too far. Okay, guys. It's a simple question. Planet? Yes, star. Okay. It's known, no. There's nothing to measure, it's known. Okay, the question says it's a very simple question. In the early 20th century, Edwin Hubble observed Andromeda Nebula. He saw stars similar to the stars in our galaxy. Fine. One star that he saw was standard candle known as V1. It's a standard candle, means you know its in luminosity. Describe how measurements of this standard candle could demonstrate that the Andromeda Nebula is not a nearby star cluster. So very simple. Intensity is equal to luminosity over 4 pi d square. Okay. So this is known since it is a standard candle. Since it is a standard candle, the luminosity is known. So you measure the intensity of it at the Earth's surface. And then by using this inverse square law, you can find the D. And then decide, and then show that that distance is extremely large and that is not a nearby star cluster. So they should be having some reference, so you don't have to decide on that. So that is going to be not more than the value that is required. Okay. So write the answer. The luminosity of the standard candle is known. Luminosity of the standard candle is known. luminosity of the standard candle is known. Come on. By measuring the intensity of the Earth's surface, by measuring the intensity of the Earth's surface and using the inverse square law at the Earth's surface and using the inverse square law the distance to the star can be calculated. Okay. Full stop. And then it can be derived. It is not a close by star, or it is not a nearby star cluster. Okay, let's go to the previous part of the question where it's told to show there are lots of stars which don't fall along the diagonal, which confirms they have passed the main stable period. So those stars are old, they have reached the end part of their cycle is what I told, right? Add on to that, there are red supergiants at the right top. There are red supergiants at the right top. And white dwarfs at the left bottom. They have allocated a mark in the marking scheme for mentioning that. There are red giant stars at the right top. These are red giant stars here. These ones. And white dwarf stars at the left bottom. So mention that. Out of the 3 marks, 1 mark is allocated for that. Okay. No, don't worry. Trigonometry is not applicable here. Do you understand? Trigonometric parallax is used for nearby stars, not for something in another galaxy. Don't worry, you will get it. You will get at least 2 marks.
So, but then, because you can't measure parallel triangle because it's small, doesn't that provide proof that it's not the answer?
Anyway, to begin with, you won't be able to find something in the background of it, right? So then how do you even begin with that trigonometric parallax? Yeah, but if you take it that way, yes, but I don't think that is acceptable. Right, then question number 33 we haven't answered, right? 33. Give a try. What? Okay. No, not the observed. What is emitted? What is emitted from that star? So this is the emitted wavelengths, the actual wavelengths. Yeah, that was emitted from the star. No, no. When it is coming towards us, it will be different. It will be more than the actual one wavelength. The star is moving away from us. So by the time it comes to us, the wavelength that we are receiving will be much more. So what we calculated here is what is detected, what is observed. Huh? Yeah. Delta lambda over lambda is 10.96. So the delta lambda is the difference. Lambda is the actual wavelength. That is equal to 10.96. So the delta lambda is cross multiply, you get 1468. What is emitted is the actual one, what the star is sending. So by the time it is reaching us, it is different. Yeah, that is actual. This is what we are reaching. What is reaching us? This is this one. This is not the actual one. This is what we see. This is exact. This is 134 is what the star sees. By the time it reaches Earth, it has increased a lot because of the redshift. So by the time it reaches Earth, it has become 1602 nanometers. That is what you see. That is a detected one. It has become 1602. It will be definitely increased if the star, obviously the galaxy is moving away from us now. So when it reaches us, the wavelength will be more. Whether speed is increasing or not, if it is moving away, anyway, when it reaches us, it will be different. Right. The spectrum of light emitted by the star Chilupi or Kilupi provides evidence of mercury atoms in the outer layers of the star. There are mercury atoms of the outer layer. The light emitted from the star is compared with the light emitted from a mercury lamp on Earth. What is emitted from the mercury lamp on Earth and what is emitted from the star is compared. The lamp contains 1.65 into 10^19 atoms, mercury atoms in the volume of given. The pressure of the mercury vapor is given. Calculate the mean kinetic energy of mercury atoms. So mean kinetic energy is given by E equals, you can use 302 kT, where K is the Boltzmann constant, T is the thermodynamic temperature. Am I right? So to find the T, I can use this equation PV equals NKT. P is the pressure, 4.25 into 10 to the power 4. V is the volume, 1.5 into 10 to the power minus 5. NKT, N is 1.65 into 10 to the power 90. K is the Boltzmann constant into T. How much is the Boltzmann constant? 1.38 into 10 to the power minus 23. Is it? So that will give you 4.25 10 to the power 4 into 1.5 into 10 to the power minus 5 over 1.65 into 10 to the power 90, and also divided by the Boltzmann constant 1.38 into 10 to the power minus 23. Is it 2799.7? Are you getting this temperature? Okay. Yeah, no, we can do that. So the mean kinetic energy is 302 kT. 302 K is 1.38 into 10 to the power minus 23 into the T is 2799.7. Is it 5.80 into 10 to the power minus 20 joules. Have you got this answer? Yes.
So you can take this 3 by 2 PV over.
Yeah, same thing. Instead of KT, you can use PV over. One line in the spectrum of light from this star has a wavelength of 576.933. Okay. The equivalent line in the Mercury spectrum produced on Earth is 576.959. Right? A student concluded from this data that the star is moving towards the Earth for some reason, and that the relative velocity of this star is about 1,400 meters per second. Did you feel that the student's conclusion is correct? Right. Without any calculation, just by looking at the two wavelengths and comparing, we can decide whether the star is moving towards us or moving away from us. Okay. Now, the wavelength that is detected from the star is 576.933, which is lesser than the actual wavelength, which is 576.959. So the wavelength is lesser than the actual value. The detected wavelength is lesser than the actual value. Means the star is moving towards us. Okay, not something that usually happens, but for some reason, yes, it is moving towards us. So his statement has two things. No, one is he says it's moving towards us, moving towards the Earth, and the other one is the speed. So the first half of the statement is correct. It's moving towards us. Understood? So to check the second half, we have to use the equation delta lambda over lambda is equal to V over C. So delta lambda will be change in wavelength, which is 576.959 minus 576.933 over the actual wavelength is 576.959. That is equal to V over C is 3 into 10 to the power 8. This will tell you the V. It's 13,520, no? Or yeah, 13,519 meters per second. So the value is wrong. Speed is wrong. Yeah. The difference, the magnitude is the value. Magnitude. So based on that, you can decide whether it is coming towards or away. Actual. Okay. So
You have to divide by actual wavelength, right?
yeah, actual wavelength.
No, but isn't actual wavelength the lower one?
Yeah.
No, there's nothing like that. Why should it be the
No, I mean in this case, no, because it says one line spectrum of the planet has a wavelength. And then the observed one is
no what is produced on the Earth is
that's the observed.
what is produced on the Earth, that is the actual one. 576.933, that is the observed one.
Yeah. So that's the observed. So the actual one is the other one.
Which one?
The 576.933.
No, that is the observed one. Yeah.
But produced on Earth, doesn't that mean it's observed on Earth?
Produced on Earth using the same thing is, that is the actual one. The one which is produced on Earth That is not moving, no. That is a stationary. So that is the actual one. Okay, so write the conclusion. The star is moving towards the Earth at a velocity of 13,500 meters per second or 13,590 meters per second. Okay. To be on the safe side, also mention. Now we told that it's moving towards us now. Based on what did you hear? The observed wavelength is lesser than the actual wavelength. Mention that. Observed wavelength is lesser than the actual wavelength. It's blue shift actually, yes. Okay. Right. Yeah, no, there's another part C. The surface temperature of this Chi-Lu P is twice the surface temperature of the sun. Okay. And the radius of this is 3 times the radius of the sun. State where the Chi-Lu P would, where would it be? State where will it be located on the HR diagram. So guys, since the temperature is double, definitely comparing to the sun, it will be on the left side. Am I right? Since the temperature is double. And then taking the, now this is the diagram, right? So here the sun is here. Sun has this, sun is somewhere here. Sun is here. It has a luminosity of 1 in the main stable period, so it should be somewhere here. So double the temperature means definitely on this side. Okay, this new star, the star that they are speaking about is definitely on left side. Left side where? Is it going to be on the main sequence or below that or what? So how do we decide that? For that they have given some radius and temperature thing. So radius is they are saying the radius of Li-Chu P is 3 times the radius of the sun. So luminosity is equal to 4 pi r square e to the power 4. So comparing to sun, radius is 3 times. Okay. Temperature is 2 times. The surface temperature of Chi-Lu P is twice the surface temperature of the sun, and the radius of Chi-Lu P is 3 times the radius of the sun. I'll ask you a simple math question. Then the luminosity of this star is how many times the luminosity of sun? Very good. Why is that? 3 square. Radius is 3 times, it's proportional to r square. 3 square is 9. Temperature is 2 times, 2 to the power 4 will be 16. So it will be 9 into 16, 144 times. So which means the luminosity of Chi-Lu P is 144 times the luminosity of sun. So then definitely it's going to fall 144 times means somewhere here, no? 100 is here, 144 may be somewhere here. So I would say it is in the main sequence, along the diagonal in the main sequence part, to the left of sun. So it's a 1 marker anyway. You can say it will be in the main sequence region, it will be in the main sequence region. To the left of sun, it will be in the main sequence region. To the left of sun is actually simple as that. Take a small break, see you in 15 minutes. Okay, question, what else? Guys, page 66. Page 66. Read the question. Read question. Page 66, we have already answered question 37, part A, B, we have answered. Part C, part C is what we have to answer. Read the part C. Okay. Right. The sun is a yellow star with a surface temperature of about 6,000 Kelvin. And in the 20th century, astronomers discovered a large variety of stars in our galaxy. The HR, Hertzsprung and Russell developed the HR diagram as a way of classifying stars. An HR diagram is shown below. The luminosity of the star comparing to the luminosity of the sun versus the temperature is given. That is what given in the HR diagram. Label the x-axis of the HR diagram. You should include approximate values. So that we have done. So 20,000, 10,000, 5,000, 2,500. It will not be a linear scale. It will be a logarithmic scale, something like this. There are 5 zones, Z1, Z2, Z3, Z4, Z5, identified on the HR diagram. They have labeled it. Complete the following table. You should match one zone with each description. Okay. Descriptions are high mass hot stars, low mass cool stars, and low mass hot stars. What is the correct zone? High mass hot stars will be what? High mass hot stars is Z1. Low mass cool stars. Low mass cool stars. Guys, in the diagram, okay. This is what you see here. This will be the supergiants and giants. So low mass cool stars means they won't become supergiants. But what is this Z4? Low mass cool stars, we can take Z5.
Mass is high.
Huh?
Mass will be high because in the stable.
Compare now low cold stars means it has to be either Z4 and Z5 on the two options. No, the Z4 is actually the temperature is high. No? It is a supergiant. Huh? Yeah. So it can be a red giant. Z4 can be a red giant, which is hot.
So
Low.
Mass is compared to the density.
Yeah, compared with the mass means here what they are referring to low mass is something similar to the mass of the sun. High mass is the, I told you there are two different life cycles. One is something comparing to the mass of sun, the other one is extremely heavier than that. So what here they mean by low mass stars is mass similar to the sun. High mass is much higher than that. So low mass hot stars, what do you think it is? Hot stars means it has to be to the left of sun. So low mass hot stars, which one it is? Z2.
The supergiants will have the mass than sun.
Sorry?
Supergiants will have
Yeah, definitely. Guys, I gave you this O-level note now. Those who have it open this, it's there in the group, which says the life cycle of a star. I'll quickly take you through that. The appearance of a star changes with time. Okay. When a star is initially formed, gravitational forces pulling the particles together. When the nuclear reactions begin, the gases expand. When these two forces balance, the gravitational force is pulling the star inwards. Due to nuclear fusion, the outward forces are trying to make the star bigger, expand. When these two forces balance, the star is said to be in its main stable period, the equilibrium stage. So if you take a star like our sun, it is in that period where the outward forces are equal to inward forces. So you don't see for the sun, it is becoming bigger or smaller currently. Okay, there is hydrogen fusion happening, hydrogen nuclei fusing together to form helium. So that is giving an outward force. And due to the gravitational forces which are inwards, that is giving an inward force. So these two forces are balanced. Okay. So what happens is, with time, when the sun is running out of hydrogen, there's not enough hydrogen to fuse. Then the outward forces will become weaker. The inward forces are strong, gravitational forces. Then the sun will shrink. It will be compressed. Okay. So when it shrinks, what happens is the temperature will be increasing a lot. So when the temperature increases a lot, the hydrogen has already fused to become helium. When such at high temperature and pressure, the helium will start fusing. So when helium fuse together, then there will be a huge outward force. Then it will become again, it will start to expand. Read that note. When these two forces balance, the star is said to be in its stable period, main stable period. A star is in this period is known as a star in this period is known as a main sequence star. It's in the main sequence. This period can last for many million years. At the moment, the sun is in this stable period. Okay. Towards the end of this period, there are less hydrogen nuclei and eventually fusion reactions stop. Gravitational forces are now larger and it compresses the star. As the star shrinks, the temperature will increase. So the high temperature will result in fusion of helium nuclei. The energy released in these reactions causes the star to expand to many times its original size. As it expands, it becomes a little cooler, and more of its light energy is emitted in the red part of the spectrum. It becomes cooler, and more of its energy is emitted in the red part of the spectrum. The star is changing into a red giant. Sometime later, when most of the helium nuclei have fused together, new nuclear reactions begin. But still, the compressive forces are larger and it will contract. This will lead to an increase in temperature so that the star again changes its color. It now emits more blue light and white light. It has changed into a white dwarf. The density of the star at this stage will be extremely high. Finally, as a white dwarf star cools, it changes into a cold black dwarf star. That is the life cycle of a star, which is similar to the mass of the sun. Okay, it becomes a red giant, and then it becomes a white dwarf, and then it becomes a black dwarf. And for a star that is much larger than our sun, it will have a slightly different path towards the end of its life cycle, which is after the stable period, it will expand into a large red supergiant. At the end of this period, as it contracts, it becomes unstable and it explodes, throwing gas and dust into space to form a new stellar nebula. From there, it forms new stars. This exploding star is known as a supernova. That exploding star is what you call a supernova. Any matter remaining will form a very dense neutron star. If it has a much greater mass than our sun, it collapses further to become a black hole. So that is the summary of the life cycle of two types of stars. Okay, right. So the question is for the next part, page 67, a 6 marker. The position of a star on the HR diagram changes as a star evolves. Explain how a star like the sun evolves as it progresses from zone 3 to its final position on the HR diagram. So guys, currently it's in zone 3. What will be the final position? White dwarfs and black dwarfs. Then it has to, from Z3, it has come down to Z2, that will be the final position. Okay, currently Z3, and then it will come to Z2. But it won't come to Z2 at once. I'm saying finally it comes to Z2. So from Z3 it goes to Z4. It becomes, yeah. So Z3 it goes to Z4. And then Z4 it comes to Z2. Okay. Right, the answer is a 6 marker. Explain how a star like sun evolves as it progresses from zone 3 to its final position on the HR diagram, 6 marker. So I will try to tell anything that I can tell which is relevant to this for a 6 marker. Okay, right. When the sun is at Z3 or zone Z3, when the sun is at zone Z3, it is in its stable period. It is in its stable period. Full stop. Gravitational forces are balanced by outward forces due to nuclear fusion.
fusion.
Due to nuclear fusion. Gravitational forces are balanced by outward forces due to nuclear fusion. Full stop. As the sun run out of hydrogen, as sun run out of hydrogen, as sun or sun or star anything, as sun run out of hydrogen, star will shrink or the sun will shrink. And temperature will increase. Star will shrink.
So what you mentioned with the gravitational force.
Yeah, we can. I mean, within the space, it's difficult to give a very detailed answer. Huh? I don't know. We will try. It's like this. There's no exact 6 points, no. So we will try as much as possible to cover the story. So you will be that will have relevant points. Okay. Patience. Let me just complete first. What did I get? The sun will shrink and the temperature will increase. Temperature will increase. And helium fusion will begin. Helium fusion will begin.
So can you repeat it?
I repeat. So what I told is, as the sun run out of hydrogen, sun will shrink, temperature will increase, helium fusion will begin. Correct? Now the sun will expand to many times its original size. Many times its original size. Temperature will decrease, expand to many times its original size. Temperature will decrease. And becomes a red giant. And it will become a red giant. And come to zone Z4. And come to zone Z4 in the diagram. Zone Z4 in the diagram. Okay. Now it is a red giant. What is next after it becoming a red giant? White dwarf. It becomes a white dwarf. Right. Then you can write. Right. Now the gravitational forces will increase. Now the gravitational forces are larger. Now the gravitational forces are larger. And temperature of the star will increase. Temperature will increase. And the star will become a white dwarf and enter zone Z2. Okay.
So that means in Z2,
Z2, yeah.
in Z2, the mass will be high.
Mass. You can't, there won't be no big change in the mass. This mass of the star will be almost, there can be slight changes due to nuclear, yeah.
The mass of Z2 and Z4 will stay the same.
If anything, it can be a decrease, but it can't be more. How can the mass increase?
Yeah, because the gravitational force increases, that's the becomes smaller.
Yeah, so the mass won't change. Okay, fine. That was question 37. Guys, question 41, page 73. Yeah, you can finally mention that it becomes a black dwarf. Yes, but I felt like it is not needed. You can also mention we wrote enough. Okay.
But the light becomes black.
Yeah. The Hertzsprung-Russell diagram shows the relationship between luminosity L and surface temperature for a range of stars. The HR diagrams below is for a young star cluster. Mark on the diagram the position of a red star similar to the sun. The appearance of the HR diagram changes as star in the cluster evolve. Explain the changes in appearance of the HR diagram as the star cluster gets older. Okay, so guys, exactly 6 marker, same question. Now the difference is they haven't marked zones, but you can give the same answer, except for referring to that zone. Same. The appearance of the HR diagram changes as a clustering in the cluster evolve. So you can mention how some stars will be going to the red giant stage, and then it will be going to the white dwarf stage. You can speak about it. Please write an answer. Okay, you can try it for homework. And part B as well. You can do it. That question, please complete it. You do it. 44. 44. Read the question. 44, page 79. Okay. Astronomers use a variety of techniques to determine the distances to astronomical objects outside our solar system. Describe how trigonometric parallax can be used to determine the distance to a nearby star. We answered this question, right? Can answer it. Explain how a knowledge of the distance to distant galaxies has enabled astronomers to determine a value for the age of the universe. Age of the universe is found using what? Hubble's constant. T is given by what? 1. No, what was the equation? T equals 1 over 1 over h naught, right? Correct now? Right. So now we can speak about that. H per second. So h naught is per second. So T will be in seconds now. So h naught is, what is the equation connecting h naught? V equals h naught into d, no? Yes. So if you sketch a graph of if you sketch a graph of V versus D, okay, then it will, the gradient of the graph will give you H naught. Am I right? So if you know the H naught, T is equal to 1 over H naught. So for a 4 marker, what are they asking? Explain how a knowledge of the distances to distant galaxies has enabled astronomers to determine a value for the age of the universe. So we can speak about distance versus speed of the stars versus distance graph is plotted, and the gradient of the graph will be giving you the Hubble's constant, and the reciprocal of the Hubble's constant will be giving you the time period. Sorry, the time of universe, age of the universe. Exactly. Yeah. So please write an answer for that. And then 50th one is a simple one. 50th part A we haven't done. Mark that. Yeah, 52. Most scientists believe 50. Oh, that's a big deal. Show that G obeys an inverse square law. So what you need to do is G is equal to GM over R square. Listen. G is equal to GM over R square, right? So that means G into R square is a constant, right? G to R square is a constant. So what you need to do is at multiple points, maybe at about 3 points, at R equals 1, check the G value and check the G into R value, G into R square. At R equals 2, check the G value, get the G into R square value. At R equals 3, check the G value, get the G into R square value. If you really want, get another point at R equals 4, get the G value and get the G into R square value, and show that all those values are approximately equal. So 3 marker, no, I feel like 3 points is enough. Okay, so to be on the safe side, even if you want, you can check for 4 points and show that the G into R square is a constant. Okay, that's how you prove that it is following that inverse square law or inverse law. You show that the product is a constant. And 52, most scientists believe that dark matter is spread throughout the whole universe. Recent observations indicate that there may be galaxies in which there is no dark matter. Discuss how the absence of dark matter in the parts of the universe might affect the ultimate fate of the universe. 4 marker. So ultimate fate of the universe, only there are 2 options I told you. Either it can keep on expanding forever, or it can expand and after a point it can contract again. So that depends on the density of the universe. Correct? So if the mean density of the universe is beyond a certain critical value, that means it will shrink back. If the mean density of the universe is below a certain critical value, then this will expand further. So please write an answer to that based on that. Okay, 4 marker. And we have done almost the remaining. There can be a few questions remaining. Please complete the 2. If there's anything in specific, you can ask me the next day. But so that's it. I'll be starting with Unit 5 papers the next day. Okay. So we'll do a couple of Unit 5 papers and after that 2 Unit 4 papers. Okay. So irrespective of what we do in the class, I believe that you are adult enough to understand that you need to do papers by yourself. I believe that minimum 2 papers you are doing a week. No, minimum 2 papers a week.
See you people. Bye, take care. Yeah, after doing unit 4 and 5, we will be doing a few unit 6 papers. There's no theory to be done in unit 6. It's the practical knowledge tested on the paper. Okay. Bye people, see you, take care.